Okay, when we are going to do our heat calculations, we should keep our heating curve in mind. At the beginning of our heating curve, we have our solid heating up, and whenever you're changing your temperature, you're going to use Q equals MC delta T. You have your liquid heating up, Q equals MC delta T. You have your gas heating up, MC delta T. But in between the solid heating up and the liquid heating up, your solid is going to melt. Okay, so when we're melting, you're going to use Q equals ML. Whereas this L here is the latent heat of fusion for the material. And different materials, just like they have different densities, different heat coefficients, they all have different heats of fusion. So that would be a number that would be given to you, and you don't need to know those numbers. When we're evaporating, boiling, changing from a liquid to a gas, or even gas to a liquid, coming back down the other way, when we're going through this phase change, so we heated up our liquid, now it's boiling, and it's going to continue to boil at 100 degrees if it's water. It's going to continue to boil until all the water evaporates, and then its temperature is going to change. So the temperature is not going to change until all of it is evaporating. When we're doing our heat calculations, what we want to do is identify where on the heating curve we're starting. So here's a couple of samples so you can kind of see how that works. So here's one sample question. How much heat is required to melt 2 kilograms of ice at its melting point to 20 degrees Celsius? So, keeping our question in mind and our heating curve in mind, we need to figure out, all right, where on the heating curve are we starting? And that's going to make our life a lot easier. So we have 2 kilograms of ice, so we have solid. So we're somewhere here in the solid. At its melting point, well, it's going to start to melt right here. So we'll go ahead and make a dot. That's where we're going to start. And then we're going to go to 20 degrees Celsius. So we're going to be about there on our heating curve for water. Okay? So what process is that? Okay, now let's think about what has to happen. What processes are going on? We have to melt the ice, so we need to use Q equals ML, and then we need to change its temperature. So we need to find the heat to melt it, and then the heat to change its temperature. So far, so good? Okay, so we're going to use Q equals ML to find the melting. And then we're going to use Q equals MC delta T to change the temperature. All right, so Q equals our mass, 2 kilograms. Okay, the heat of fusion of ice, we would look it up. When we look it up, we find that it's 334,000 joules per kilogram. That's a lot of heat. So when we multiply that out, we get 668,000 joules. Okay, this is to melt it. So this is the melting stage. And then we're going to go Q equals MC delta T to heat of fusion, or the heat capacity, the C of water. That's what we're going to use. The C for water is 4186. Ice and steam have different heat capacities. So those are on the haiku page, and you can look those up. Times the change in temperature. Okay, so what temperature did it start at? It was at its melting point, so it was at 0 degrees, and then it went to 20 degrees. So its change in temperature was 20 degrees Celsius. So when we multiply these together, we get 167,440 joules. Okay, so what do we do with these two numbers? Well, some of the heat was used to melt it. This is the heat to melt it. Some of the heat was used to change its temperature. So all together, what do? We take those two heats, and we add them together, and that will give us the total heat. So add 668,000 to our 164,000 or 167,000, and we get a total of 835,440 joules, which is 835 kilojoules. So if we move that decimal 3 places to go from joules to kilojoules, we get 835 kilojoules. So that is one sample problem. Okay, same idea. We have time for one more problem. How much heat is required to completely evaporate 3 kilograms of water that start at 20 degrees Celsius? This is similar to boiling your macaroni and cheese water dry. Okay, so it's going to start here. It's going to be a liquid, so it's going to be at 20 degrees Celsius. And then it's going to heat up, heat up, heat up, heat up. And it's going to boil, and all you want to do is evaporate all of it. So it's not going to all be in the gas stage. So here's where you're starting, and here's where you're ending. So what processes do you need to go through? You need to change its temperature. So you use Q equals MC delta T. And you need to evaporate it. Okay, you need to evaporate it. So what temperature is this final temperature? Well, in this case, it's water. So this is going to be 100 degrees Celsius. If it was a different material, it would be a different gas. Okay, so we're going to go Q equals MC delta T because we're changing our temperature. Now, how much are we changing our temperature? It's starting at 20 degrees and it's going to 100 degrees. So we're going to take our mass times 4186, the heat capacity of water, times the change in temperature. Is going from 20 to 100, so that's 80 degrees. And that's going to give us the heat to change its temperature. Then we need to evaporate it. So we're going to Q equals ML. 2 times, now the heat of vaporization for water is a huge number. It's 2.26 times 10 to the 6 joules per kilogram. Oops, these are 3s, aren't they? We changed the amount of water we were using. We're using 3 grams of water, not 3 kilograms of water, not 2. So the mass of our water is 3 kilograms. Okay, so we get our 2 heats, and we get 1.005 times 10 to the 6 joules. That didn't show up very well. That's a 6. And we get 6.78 times 10 to the 6 joules. So to get the total amount of heat, we just take and we add those two together. And we get 7.78, pretty much 7.79 times 10 to the 6 joules. Okay, so that's kind of what we're looking for. You want to keep this heating curve in mind and figure out where on the heating curve are you starting and where are you ending, and what processes do you need to go through to get from where you're starting to where you're ending. Alright, we're going to practice this more in class, so good luck.